Today we will learn why many structural members like beams and columns have cross-sectional shapes like an eye, H, C or tubes rather than solid squares or rounds. Consider a plate submerged in a liquid. The pressure of the liquid at a distance y below the surface is given by P equal to gamma times y, where gamma is the specific weight of the liquid. The force on the area dA at that point is dF equal to P pressure times differential area. The moment about the x-axis due to this force is y into dF. The total moment is measured from this equation. This sort of integral term also appears in solid mechanics when determining stresses and deflections. This integral term is referred to as the moment of inertia of the area of the plate about an axis. Consider three different possible cross-sectional shapes and areas for the beam RS. All have the same total area, and assuming they are made of same material, they will have the same mass per unit length. For the given vertical load P on the beam, which shape will develop less internal stress and deflection, and why? The answer depends on the moment of inertia of the beam about the x-axis. It turns out that section A has the highest moment of inertia because most of the area is farthest from the x-axis. Hence, it has the least stress and deflection. For the differential area dA shown in the figure, the inertia about x, y, and z is given in these equations, where J0 is the polar moment of inertia about the pole O or z-axis. The moment of inertia for the entire area are obtained by integration, such as shown here. The moment of inertia is also referred to as the second moment of an area and has units of length to the fourth power. For a given area A and its moment of inertia, Ix, moment of inertia about x-axis, imagine that the entire area is located at a distance kx from the x-axis. Kx equal to under the root Ix over A. This kx is called the radius of gyrations of the area about the x-axis. Similarly, ky and k0. The radius of gyrations has units of length and gives an indication of the spread of the area from the x-axis. This characteristic is important when designing columns. For simplicity, the area element used has a differential size in only one direction, dx or dy. This results in a single integration and is usually simpler than doing a double integrations with two differentials such as dx and dy. Considering this example in which a shaded area is defined through a function is given in this figure, and we need to find the moment of inertia of the area about the x and y axis. So following the solution steps, first we know this equation for moment of inertia about x-axis. Express the differential area in terms of y and then replace it in the above equation. We get the moment of inertia about x-axis 2.13 meter to the power fourth. Similarly, the moment of inertia about y-axis is measured through this equation and it is equal to 4.57 meter to the power fourth. In the above example, it would be difficult to determine Iy using a horizontal strip. However, Ix in this example can be determined using a vertical strip. Thanks for watching.